The last three lectures of this section deal with electromagnetic radiation. You're used to electromagnetic radiation. That is the radiation that makes up radio waves, microwaves, light waves, frequently abbreviated EMR. And it turns out that electromagnetic radiation sort of follows quantum type rules in that it can exist both as a wave and a particle, and the only way you know which one it's going to act like is by observing it. In this lecture, we're going to deal with waves, and you all know what a wave is. A wave is an oscillating function that goes up and down or back and forth in a periodic fashion, or it looks like a snake. And there are various terms that you need to use. The top of a wave is called the peak. The bottom is called the trough. The amplitude is from the midpoint between the trough and the peak, and it's, quote, the height of the wave. And the distance between peaks is the wavelength, and this one we're really concerned about, so we're going to give it a special symbol, the Greek letter lambda. Wavelength is lambda, and the base unit is in meters, but all of the metric prefixes can be used to describe the wavelength. Whenever discussing waves, you also have to talk about the frequency. The frequency is how many waves pass a fixed point in 1 second. The more waves, the higher the frequency. The fewer waves, the lower the frequency. And since frequency is so important, we give it its own symbol, the Greek letter nu. And the units for frequency are per second, or 1 over a second, which is the same thing as seconds to the minus 1. And just to give it a name, we call it a hertz. And this is named after a physicist, not a car rental company. For any wave, the speed of the wave is equal to the wavelength times the frequency. But to put it into symbols, because I hate writing words out, lambda nu equals speed. And for electromagnetic radiation, the speed of the wave is a physical constant. It is 300 million meters per second, which is given the shorthand abbreviation C. And yes, this is the same C that you would find in the world's most famous equation, E equals mc squared. We are now able to say that lambda nu equals C, which equals 3.00 times 10 to the 8th meters per second. This is definitely note card material. This means that lambda and nu, wavelength and frequency, are indirectly related. If I increase my wavelength, I have to decrease the frequency. If I decrease the wavelength, then the frequency has to increase. Why? Because lambda times nu equals C, which equals 3.00 times 10 to the 8th meters per second. That is a constant. So that means that every wavelength of light, of electromagnetic radiation, has a very specific frequency, and every frequency of electromagnetic radiation has a very specific wavelength. And since both of those last two statements are bold type, red type, underlined, and italicized, probably pretty important. So if you take a look at the electromagnetic radiation spectrum, starting from the left-hand side, if you look at the bottom of the long gray line, you see that the wavelength increases going from left to right, but that the frequency decreases going from left to right. And that's because they're inversely related. Also note that along that spectrum, the visible spectrum, the light that we can see, makes up a very small portion of the entire range. So now we can do some simple calculations. The first one is, what if you had a wavelength of 4 times 10 to the minus 3 meters? What's the frequency going to be? And to tackle any problem, you always start with, what do we know? Well, we know that C equals lambda nu, that C is 300 million meters per second. We know that the wavelength, lambda, is 4 times 10 to the minus 3 meters. We have no idea what the frequency is because that's what the question is asking. So now, just set the equation up because we have two of the three variables. And now it simply becomes, as some mathematician once said, plug and chug. Divide both sides by 4 times 10 to the minus 3 meters. So that this appears from the right-hand side. This is what frequency equals. Do the math, and you get 7.50 times 10 to the 11th per second as the frequency. Example 2. One of the local radio stations, WKBK AM radio, broadcasts at 1290 kilohertz. What's the wavelength of the signal? And note that this is in kilohertz, but you really want the frequency in hertz. That's a hint. Go. The answer is 233 meters. How did we get this? Well, what do we know? We know this equation. We know this is the value for C. We're given that this is the frequency, but as stated initially, the hint is this is in kilohertz and you want it in hertz. So you do the conversion, remembering that there are 1,000 kilohertzes in 1 hertz, and you get 1290 kilohertz equals 1.290 times 10 to the 6th hertz, or 10 to the 6th seconds to the negative 1. We know that lambda equals lambda because that's what we're looking for. Put the values into the equation, solve for lambda, and you get this number on your calculator, but the answer should only have 3 significant figures, so you get 233 meters. The final example, what's the wavelength in nanometers of the yellow light that a sodium vapor lamp, those lamps you see on the highway, if the frequency of this light is 5.10 times 10 to the 14th hertz? Go. The correct answer is 588 nanometers. How did we get this? Well, once again, what do we know? We know the basic equation, and we know the value of C. We know the frequency. We don't know the wavelength. Set the equation up, plugging in the values where appropriate, rearrange it to solve for lambda, and you get 5.88 times 10 to the minus 7th meters is lambda, but the question asks for the answer in nanometers. We know that there are 1 times 10 to the 9th nanometers in 1 meter. So we set the equation up to do the conversion. 5.88 times 10 to the minus 7th meters times 1 billion nanometers per 1 meter. Notice the meters will cancel out. And you get 5.88 times 10 to the 2 nanometers, or 588 nanometers. So in review, wavelength, lambda, is a distance between the wave peaks. Frequency is how many waves pass a point in 1 second. Wavelength times frequency equals the speed of a wave, which can be written as lambda nu equals speed. For electromagnetic radiation, speed equals C equals 3 times 10 to the 8th meters per second. So you can write the equation this way, which means that lambda and nu are indirectly related. If one goes up, the other goes down, and vice versa. And that takes care of light as a wave. In the next video, we're going to discuss light as a photon and also begin to discuss and calculate how much energy is within each specific type of wave.